How's it going, everyone? Welcome back. Rather unfortunately, as I went to click the button to uh, start my webcam, I accidentally clicked the end stream button instead, so there might have been a little hiccup there. So sorry about that, but it seems like everything's back up and working. All right, so last time we had to we were trying to figure out a circuit to balance those batteries, and we really didn't do anything. I spent the whole time researching stuff and not really getting anywhere. I learned a lot, but not a solution. So, excuse me. So today we're going to be doing more of that because this is one of the last things that we need to, like, major things that we need to figure out. I found another article that was semi-interesting. It's for a battery balancing method that's different than the one we're using, but it will at least allow us to. It helps with or what is it? It gives tips on selecting switches, which is the thing we were having trouble with. So I'm going to look through this and start with that and see if we can pick something out. Because if we can pick out a switch, I think we can get there. And as far as the capacitor goes, we'll just pick a generic footprint kind of thing, and hopefully then we can switch it out later if we need to. All right, so I'm going to turn the music back on. As usual, bounties are always in effect. And let's see if we can figure out what's going on here. The two cells are identical. There's always a slight difference in the state of charge. Balancing the lithium-ion batteries. I think they're going to, this is a Infineon paper, I believe. So they're going to recommend their own MOSFETs, which is fine. Individual cell voltage must be monitored to allow cell balancing. When the cell-to-cell voltage variation is greater than a specific value, the cell balancing circuitry is enabled that gradually matches the voltages of the individual cells. As stated above, the MOSFET, along with the series resistance, bypass part of the current around the cell. So this is the method that a lot of people have used, and they make chips for, that basically just drains the cell that's too high. So this really isn't what we want to do, but we might be able to use the same switches. Let's see here. There was something else I learned about too. I was talking to somebody about it. So let me see if I can figure out something else here. Ooh, what is this? It's an expensive part, because I think it's for high current stuff. I'm going to use something like this too. So effectively, we're going to have to, either we're going to have to use a pair of MOSFETs for each switch, kind of like what is recommended here, or we're going to need to use some sort of relay. The relay option seems more straightforward. We could find something in a single package that does it, but we would likely it's likely too heavy duty is usually the problem. Looking up something here. There's a lot of stuff here, but it's all for like telecommunications type devices, which is really interesting. SPST normally open. We need an SPDT. 2 remaining. Yeah, that's an expensive switch. Jeez. Oh, interesting. There's a few of these. Wow, they're expensive though. All right. Quantity 1, Toshiba. What's this part look like? So this has potential. Cathode, drain 1, drain 2, drain 3, drain 4. I'm assuming 7 and, like, if you activate this, 7 and 8 then are connected together. Telecommunication, measurement equipment, security equipment. Interesting. I wonder if they have a recommended circuit or something. I wonder what about this makes it useful for telecommunication stuff. Wow, they get expensive fast too. Look at that. All right, let's go back before we picked out a specific type of switch. Let's take out the circuit. Okay. How many are there? 310. Pricing. What's our, like, dirt cheap options? SPST normally open. Ideal for AC load control. Interesting. At least they have wiring diagrams, though. That'll explain a little bit. Yeah, you definitely have to have a resistor on everything. That's fine, though. I can see something like this working, actually. So that's a pretty common one. That one not so much. So normally open is pretty common. Let's see what this looks like. Yeah, these are expensive too. Let's see here. I think something like that. Like I think we can get a working solution out of this. It's just the only thing I don't like is it's expensive, but we might have to just deal with it because the other option is we could look into a selection of MOSFETs that do the same thing. But I think we do have to. I'm gonna need to know. So, unfortunately, I really don't understand MOSFETs that well. Like, I understand the basic concept, but I can never remember the N type, P type, enhancement, and depletion type, like what all that is. So maybe I'll look that up real quick. Here. Pull this back up. So we're going to drop it in here somewhere. Okay, so depletion type is normally closed. Enhancement type is normally open. So if we use the two different types, then we don't have to invert the signal. So that would be a good start. Then as far as the N type and P type, hold on. I can't. I apologize for doing this off screen. I have to. I don't know if I can show. There's certain things I don't know if I can show on screen just because of copyright or just because there's ads scrolling on them. I don't know what ads are going to pop up and that kind of thing. So let's see here. trying to find the difference between, and like I want to understand. I think I can figure out how to use it, but I want to understand like specifically what the intended application is of N type versus P type, so that I can pick the right thing. Oh, interesting. Okay. So it seems like N type is actually preferred in most cases. Well, maybe not. Hold on. So the main difference between N and P channels, the N channel usually goes to the ground side of the load, the device you're powering, the P channel to the VCC side. Okay, so I've been doing that this whole time because I thought that was how that worked. That makes sense. So if I pull this up on screen real quick. Give me just a sec. This graphic right here. N channel usually goes below, and you like pull it low. And I believe the gate to source, it requires the gate to source voltage to work. And then it matters too, this is a dotted line, meaning this is a enhancement type? Yes, enhancement type is a dotted line. Okay. Still not understanding that fully. I'm going to need like a serious truth table to figure this out. All right, so why do you have to connect one negative to the other to the positive side? So enhancement type turns on if there's sufficiently high positive voltage on the gate relative to the source for logic. Level MOSFETs are typically 3 to 5 volts. Activate it. Oh, okay, hold on. So I think the way these things work is it's the measure of the, in every case, it's the measure of the gate to source voltage. So the P channel, your source is up here, the VCC, so you need a difference in voltage greater than the required for this source to gate right here. And then enhancement depletion is normally on or normally off. So for the N channel, they reference the other side, the ground side. Okay. I think I'm starting to understand this. So I think it's going to matter for the switches which ones we are using. Oh man, I really hope I get this right. Huh, interesting. Okay, so I'm just trying to think through this because the capacitor is basically moving between the batteries, and we're switching it on and off, the different switches. Oh, this gets weird though, because on the higher battery, the references are all over the place here. Like so like in the P channel, your reference is VCC, and in the N channel, your reference is ground. Ground is easy, but depending on what battery we're connected to, this actually does change. Like the reference is weird compared to where the micro is going to be at. So I don't know if I can get this to work easily. Also, if you stop by tonight, make sure you say hi. Wouldn't mind chatting with someone. Okay. Let's think through this then. We're going to have to connect it to the top, the 8.4 volt battery, and turn it on. Be able to turn it on and off. I might have to do multiple of them. That's what I'm thinking through here. In order for this to work, I'm going to have to do... Oh, wow, this is hard. Because we're going to need different levels, right? So the top battery is going to be a P-type on up there, I think. Yeah, it'll be a P-type. But the reference, like the highest voltage we'll be able to go through with the micro is 3.3 volts. So our reference is going to be way off. So we need an NFET driving that line. So we're going to need multiple levels because we're going to have to shift everything up and all that. Okay. I think what I need to do is tinker around with this, get it right for one of them, one of these series circuits, and then I can do... Oh, excuse me. And then I can do the other one. And I'm going to have to double check all this work and have someone else look over it just because it's going to get so confusing. That's all right, though. I'm down for it. Okay. So I'm going to keep this up, these articles that I have. Actually, there's probably a really important table I need to pull up here. Here, I'll get a screenshot of it out of this article. All right, this right here. So if I look at this table and look at the things I've already been looking at, maybe I can figure out what's going on here. So enhancement versus depletion, what is that again? So more common, enhancement type is not conducting when the gate source voltage is 0. Okay. So enhancement type is normally off, which we see here in this, we see right here. Source is 0, and then it's plus V, that goes high. When it's minus V, that's off. Okay. The P channel enhancement, when you have the line high and your source is high, that means the gate source voltage is 0, so it's normally off as well. The voltage from gate to source is negative VE, it's on, and plus VE. That means if it's plus VE, that means the gate is higher than the source. Okay, got it. And I know that I'm waving my arms all around. How's it going? I'm trying to figure out MOSFETs, which are a form of transistor, I believe. I think they're a form of transistor. And they're really confusing because there's a lot of different types. Okay. So depletion types are normally on. So if that gate source voltage is 0, then it is on. Gate source plus V. Wait. Hold on, I don't think I understand this table. Source, and then if it goes up, it's on. Okay. For a depletion type, if it's 0, it's on. It has to go below to turn off? That doesn't make sense. Or I guess it does. I guess there's not many cases where you'd use a depletion type. But clearly I have missed something in the understanding there. So why would you use the depletion type? What is that scenario? Is an N... They said... I think they... Okay, hold on. No. I thought an N-channel depletion was the same as a P-channel enhancement or something, but that doesn't seem to be true. It's just the opposite of it. Alright, hold on. So for N-channel, we have... Please excuse my horrific drawing here. Oh, wait. Okay, hold on. So if you take the N channel and put it on top of the load, hold on, they've got an example here. I'm just gonna new screenshot. If you were to do this, I think then that makes sense. That N channel depletion type, because your gate voltage needs to be below your source voltage in order for it to work. That's the easiest way to make it work. So I think that makes sense. But normally you'd want a P channel instead, because the situation is just easier to work with there. A P channel enhancement type in that scenario. So this drain and source would be flipped, so the source would be up top. So P channel enhancement would turn on when you lowered that voltage. be off if that went up or it was the same. What about a depletion type? Normally on, still on. Okay, so there are ways that you can like do this, and it's going to get really confusing. We are definitely going to need this chart I have. Okay. All right, we're going to use this. We're going to start picking things out, and hopefully we can get there. And we also have to do some ridiculous like level shifting things because that's just how it is. Okay. Yeah, I'm definitely going to have somebody review this when I'm done just to see that I've not made an error here. All right, so I said I need to do one of these series circuits. So this line right here is still going to be connected, but other things will be connected to it. We have the grounds there. That's fine. How are we going to do this? Let's take this. No, let's take all of this. Slide this down. Hang on. All right, there it went. Hopefully this doesn't freeze too much. I think I'm going to turn these sideways so that they're vertical because that'll make it easier for me to understand. I'm just going to redo this whole thing. So, if you have any tips though, or see anything along the way where I make a mistake, let me know. Because it will matter. Okay, oh man, I hate to delete this, but I think I gotta. Well, maybe not. Hold on. Is there a way to like rotate this? Because that would be awesome. Nope. Alright, I think I just gotta start getting rid of wires. All right, if we go 90 degrees. Nope, I want to go the other way. So 270 degrees. All right, let's start with this. Get this way down. Give us some room. And then, let's see, this. Slide, oops. Slide this down. And we're just going to move it like all out of the way, everything. We'll come back to it. Okay. I guess this one can come up here too. Oh, eventually. All right. So we need to connect our grounds. Just have those up here and running. And this side goes to ground. All right, and then we need, this is the wire that goes between them. Okay. Now, we need to figure out how to do this. I guess we need a capacitor of some sort. Let's just pick one out from our bill of materials, and then we'll probably pick a different one later. What's the biggest capacitor we're using so far? 10 microfarads? I mean, that sounds like it could be a fun size. Microfarad. Yep. It's a big 1206 capacitor, geez. Alright, let's use that one. I noticed the internet was kind of slow today. I've been having issues with it, so I apologize if the stream has issues. It seems like it's running okay, but let me know if there is issues. I don't know if there's anything I can do about it, but I'll try. Okay, single capacitor right there. And we will rotate this 90 degrees. Okay. And we're going to turn off the name for now. All right, so we need a switch that connects this bottom side to this line and then the top side to this pin up here. So I guess we can run a wire out for this reason. And then we need to do the same thing to something that puts it down here. So I think enhancement types for the lower one makes sense. Well, the top side could be a little weird. Yeah, we're going to need 10K resistors and things. Okay. Let's just figure out the first one. The first one's easy, connecting to ground. Ground just needs an enhancement type NFET. NFET meaning N-channel MOSFET. If we look at our chart here, N-channel enhancement, source is 0 to be off, plus it'll be on. Okay, that's acceptable. I know we have some that we've used so far. The question is, okay, we've got one here, so let's just use this one that we've already been using. BSS 138. That's a pretty common one, actually. Do we not use any other NFET types? Wow, really? Okay. I think learning this, though, I need to go back and check out everywhere I've used one, because now that I've looked at this table, I probably need to double check all of my work again. It's fine, it happens. All right. We're going to place this one. All right, it is an enhancement type. And I am going to move it up and do a whole resistor network thing here too. All right, so that connects there. Oops. That connects there. This is a wire that'll go somewhere. And then 10K resistor, we've definitely used that before. Here we go. So I think obviously the resistors I think will be fine, but everything else like the capacitor and the FETs, I might go back and change before this is over, like what type of part, or exactly what part it is, but at least this will tell me the type that I need. I'll have a working circuit that tells me N-channel, P-channel, enhancement, depletion types, all that. All right, let's rotate this. Turn that off. Okay, drop this in here. All right, so what this will do is hold it low, which in this case, sorry, I'm looking for So 1 is our gate, 2 is our source, 3 is our drain. And this is an N-channel enhancement. So the gate source, when this line goes high, will turn on, but normally it's pulled low, so it'll be off. Okay. Now I need one when connected here. So that's okay. This is going to become fun. That was the only easy one. The rest of these are going to be tricky. I wonder if I can put a comment or something in there. Maybe we need like a notepad or something. Sorry. That's stuff from the last project. Okay. Q21. Actually, you know what? Spreadsheet's better. I've just decided. How do you add a sheet in this? Fine, we'll just... Alright, Q21. On high, off on low. Actually, we probably want to do the other way. Do a truth table of high and low. On, off. Okay. So now, I know that. So now I got to make the next one. So connected to this line. We want it to turn on when the line goes in the opposite state, right? When the line goes low. Hold on. This is already confusing my brain, and I'm even trying to think about it in little pieces rather than the whole thing at once. Alright, so on this line, when it drops down low, we want it to turn on. So when the voltage of the gate source becomes negative, we want that to become on. But when it's at 0, we want it to be off. So we want a P-channel enhancement right there. Wow, that's wild. But I guess that makes sense. Well, no. Because P-channel would be referencing not that voltage, but the voltage at the bottom of the capacitor. Which isn't guaranteed to be something. It needs to be referenced off the batteries. But if we connect the other side, then that could work. I think. Alright, so we're going to need a second one of these N-channel FETs. Because we're going to need a way to pull the line low. Oh, no, we need... hang on. Well, let's start here. Let's start with just what we need right here. So if I put a P channel connected to this line, oh, maybe I do go an N channel. I knew this was going to be hard, and it's already... Like, there's so many possibilities here. I'm sure somebody who understands this stuff or has a lot of practice with it could just whip something together real fast. Hopefully I'll be like that one day. Probably a P channel. Do we want a depletion? No, we want it to turn on when it goes low. Well, we can worry about that, though, later. Hold on. I'm trying to think through this. I need like scratch pad or something where I can just draw this out real quick. Want it to go low. Be able to drop down. So P channel. Yeah, okay, P channel enhancement will work. Okay, hold on. I think we have that somewhere. That's too big. There's another P channel that we use somewhere. I thought. No, we might have to find one. I think everything I've used so far is like heavy duty. Hang on. Looking up one of the ones we already used. Oh, yeah, that's too much. Dang it. All right. All right, I guess I got to find a new one. In stock, active, P channel. Pull this up here real quick. It's going to take a long time just to get a little bit of the ways. What the heck is this? Wow. I want something in a package like this. I like how I pick P channel and it's like showing me an N channel right here. Like, come on. Clearly this FET type thing didn't register. There it goes. Okay. And then I need it to be an enhancement type. Although I think most stuff is enhancement, so it's probably not going to be that big of a deal to find one. do something like this. This is enhancement type. Okay. Channel. I need a threshold voltage. Ugh. That's the breakdown. What's the voltage where it activates? Does it have to be 20? Because that's intense. No, that's max. 3 volts at 1 milliamp. Or is that the change? Clearly, I don't know everything I'm looking at. Otherwise, this would be easier. All right, we need something that's I can buy in low quantities as well. Is there an obvious like SOT 23 or something? Because that would be awesome. This one. All right. Let's try this. Gate threshold voltage, 3 volts. Gate source voltage plus 12 volts. I think that's a limit though. All right, hold on. I can figure this out. I think the way this is worded is basically plus anything. Like, if we look, oh, what is this? No. If we look here at this table, where it says voltage gate source, like, plus VE. What is VE? Is that actually a certain thing, or is that just like plus anything? It starts to let current through. Gate source voltage, drain current. Okay, so the closer you get to 0, I guess the closer it gets. This is its leakage, basically. All right, I can get there. This is the resistance. Oh, okay, interesting. So it doesn't take a whole lot, apparently, a voltage difference to make it just like max out. All right, I think this one would work. I'm surprised I hadn't gotten something already. I remember seeing part number similar to this, so I'm looking real quick. All right. Yep, doesn't look like it. I wonder if this part's even available. Because this is the other thing, is we're going to have to find parts that already have models made. Ooh, it does. Oh, thank you. All right, now to understand what exactly is going on here. Data sheets for days. All right, pull this off to the side. So what pin is what here? So P channel, this is the source right here, down below. And the one up here is the drain. Is that a good way to be able to tell? Yeah, kind of. And the gate source voltage is what needs to change. So I think our best chance is having this tied to that and then tying that one up here. Okay. And that goes there. This comes out here. And then I'm going to turn this part number off. Well, no, I'm not going to do that. I'm just going to move it out of the way. Okay. All right, and then this needs to be connected through a 10K to here. Hold on, I gotta just place the part so that it gives a valid resistor. Nope. Valid resistor number. All right. And that goes there. Okay. So it's effectively going to pull up, and then whenever it goes down, that's when it will, when it drops low, that's when it will be a turn on, I think. If we pull up this table again, that's the gate. Or no, this is the gate, this is the source, this is the drain. So as long as the gate, this is a N channel enhancement type. Gate to source is off. And it needs to go high. Oh, oops. To turn on. Oh, well, that's not going to work then, is it? Well, we would rather have a depletion type? I don't know, it is going to work. Yeah, when you go negative voltage, okay, it's a P channel enhancement. I'm looking at the wrong table. P channel enhancement, yeah. So when that goes low, it's going to turn on. Okay. So then how to turn it on? Probably with an NFET to drive that low. But it really needs to be inverted. So if the line goes low, we want it to turn off. I can't wait to work this whole 2 hours and only get like a little bit through this. You know what I really need is just like some of these like on the table here with a breadboard and some power sources just to see if I can get it to do the things I need it to do. All right, so according to this, when this line goes to ground, this will turn on. So how do we get it to ground? Do we use another enhancement type? No, because it'll be too high. To go low to turn on. So we need here. Let's move this back and move this out. So we need this to connect to ground. Turn it on, and we needed to do that whenever the line goes low. So it normally off. Is there something that does that? A P-channel depletion type, right? It's positive, then it turns off. Yeah, that seems like it would work. A P-channel depletion type. So I gotta find one of those. Is there a better way to do this? Is that a regulator? No. Well, kind of, not really. This is we're trying to put together a network of transistors to cycle this capacitor back and forth between these two batteries. So these are connectors for the batteries. That way we can balance charge between them. So we're trying to come up with a way to connect this battery appropriately between the two, or connect this capacitor between the two. That'll make it work. And these are just, so this is an NFET enhancement type MOSFET. This is a P-channel, N-channel, P-channel enhancement type MOSFET. And then I have a truth table here for effectively what is happening between them. What each one does when the gate source voltage is in a certain state. I don't know if you can easily search like enhancement or depletion types. Because depletion types are not even that common. So there might be a way to do it without using those anyway. Technically for the charging circuit, but it's used in both cases. It's going to be running all the time during consumption and during charging just to keep the batteries balanced, because in both of those cases they can become unbalanced. You know, this might honestly make sense just to use this NFET type transistor for everything. Well, actually, I can't use it for everything. I don't think. No, I couldn't. But use these enhancement depletion types for everything, and then just an inverter somewhere. Well, but our voltages are still odd. So we'll still have to use that. Yeah, okay. All right, so let's try something here then. Let's use the same N-channel one. Drop that right there. And then we're going to need our same resistor. All right, so here's our signal line. So when it goes high, this turns on, drops this low, which makes this voltage really low, or negative on this P channel enhancement, which turns that on. So when this turns on, when this goes high, this turns on, which drops that low. Which turns that on, which is not what we want. So basically, effectively, both of these turn on at the same time. So we need to invert this signal right here. So how, or what's the best way to do that? Oh, what if we used another FET, actually? The reason I didn't want to use an inverter is because I'm worried about driving this thing from... I'm worried about... Let's see. I think this could work, but I'm worried about driving this thing from like 3.3 volts or something, because I don't know what's going to happen when the chip turns off. Or even 5 volts, because when I kill the power, like, what's going to happen there? So I'm trying to do this without like a reference of like from the 5 volt or 3.3 volt lines. I want it to be solely based on the batteries, because that way it'll always be in a corrected state. So this is going to be, so I need to rename this Q23. And then if I use another one of these, I think that inverts the logic. Oh, this is becoming fun. This is going to get so confusing with all these labels. And I think I need to change this R37 pull down resistor to be high, actually. All right, and then I need this same resistor right here. All right, R38, and this is going to be Q24. All right, and then this resistor actually needs to go up to this side, or go to this? I think it goes to this. So this is going to get awesomely confusing. All right, let's just see what happens here. So let's start with Q24. All right, so on Q24, when this goes high, so it's pulled low, that's off. When it goes high, it turns on. Then Q23, so when this turns on, it pulls this line low, which is going to turn Q23 off. So when it goes high, Q23 turns off. And then that leaves Q22. So when this goes high, this turns on, which turns this off. Q22 is a PFET, which is pulled to that. Oh, it's all gone wrong. P channel enhancement, which gets pulled down to 0, so nothing happens. Oh, wait. So when this, okay, let's go through this again. When this goes high, this turns on, pulls this line down to ground, so that turns this off. So this line is pulled to the source, so that turns this off. So Q22 turns off when it goes high. Now if we do the opposite of that, if this goes low, then this turns off. This gets pulled up to that voltage, away from its source. So this turns on, pulls this down to ground, which drops it negative, and turns this on. So Q22 turns on. Okay. So what we care about is that Q21 and Q22 have opposite states. So according to my little chart that I'm putting together over here, when Q21 goes high, or when this line right here goes high, and I need to connect these now that I know that it's going to work. Okay. When this signal goes, when the signal goes high, this is going to turn on, but Q22, the other one connected to the capacitor connecting to this other side, is going to turn off. Yeah, okay. And then when it goes low, this one turns on and this one turns off. So then the capacitor is connected to this middle line here. Okay, this is really confusing, and I could definitely lay this out a lot better. But we're in the right place. Oh, man. All right. Good news is the other side's going to be a lot harder. Though really, I guess I could just use a variation of the same circuit to make it work, so. So basically, I'm going to have to use these enhancement type NFETs to control, for the control lines, and then, yeah. Interesting. So for up here, we want C32 to flip between this line and this line. I think I'm going to need another one of these. There's probably like, man, this is why that relay option was like probably such a good idea if it wasn't so annoying, like in terms of size and being heavy duty and everything. Oh, and being expensive. I forgot about that part. But all this stuff's going to be more expensive than one of those chips, probably. Interesting. Okay, so I think we can figure this out. So let's get one of these. And we need this to connect here. I think what I'll probably end up doing is making a second sheet for this other set of batteries. All right, and this is Q25. There's gonna be so many parts on this to make it work. All right, that remains to be our signal line. And then we need an NFET to pull it down. I guess I should go ahead and put this in here as ground. So the capacitor is connected to ground when this turns on. So we want it when this turns on. That's not the case. This turns on with this one. There's a good chance that I go through a few iterations of the circuit here, even before I get too far. I'm just trying to understand how it all works. Maybe I can find a way to simplify things. All right, so we need an NFET. I think we're going to need the same thing that we have here, basically 2 NFETs. All right, so let's do that. And that gets pulled to ground. Man, it's a good thing I deleted half the batteries at this rate. Okay. And I think we need resistors for these. Yep. We need like 3 of them. 1, 2, 3. Okay. Oh, this might be backwards. Yeah, I think this is connected on the wrong side. Ah, dang it. This is going to get confusing again. But that goes there. And this goes here. All right, and then the resistor. Just gonna turn these off. No, that doesn't go there. Hold on. That goes there. Okay. Now what is this about? Oh, I guess not connected, technically. Why isn't that showing up as connected? Oh, because that's technical. Okay. Right. All right, I think that's right, because that needs to drop low for that to work. For a P channel enhancement, yep. Okay, and then this one. What do we say on that? It needs to be pulled up. And then this one pulled down. Oops. All right, so let's go through this logic then. We want this to have we want Q25 to have the same truth table as Q22. So when this line goes high, this turns on, pulls this low, turns this off, which pulls this to the gate, matches this, the gate source is matched here, so 0 volts, which turns that off. Okay. 6, 7. All right, so when this goes high, Q27 turns on. Pulls that low. There's a fly. Meaning Q26 turns off. Which means that's pulled there and turns Q25 off. All right, and then the opposite of it. So when this goes low, Q27 turns off. Which pulls this one high, which means Q26 turns on. Which then means that it pulls this low, so this is that negative gate source voltage that we want, and Q25 turns on. All right, cool. So that gives it the same truth table as this one here. Now, ooh, excuse me. Now we got to figure out how to emulate this one right here, Q21. I think it's going to be a very similar circuit, at least just as hard. I think we need the same PFET. This is here. And then this goes over here, and hold on. I just love how complicated this is getting. It's like practically unreadable. All right, so we need the same resistor. This is going to be Q28, I guess. And then okay. This is getting absurd. But I love every bit of it. All right. Okay. So when this goes low, it'll turn on and it's pulled high to that. We want it to activate when it turns on, right? When it's high, we want it to turn on. We want it to do the same thing as Q21 does. On. Yes, so I think if we do a single N type, then we get where we want to go. Because we need to be able to pull it down. I'm just going to put another ground port right there. This is Q28. The fact that we're up to Q28 is awesome as well. It means we have an Q29, sorry. It means we have an awesome number of transistors on this board. All right, and this wire goes out to here. And then we have, turn that off so I have some room. And then we have the same resistor that we've been using the whole time. And we drop this right here, I think. And pull it low. Okay. So Q28 and Q29. All right, so when this line goes high, Q29 turns on, pulls this low, which turns this on. Right, because P channels turn on when that voltage goes negative, which it will do because it'll get pulled to ground. Pulls that low, turns that on. And then when this goes low, this turns off. This gets pulled up to the source and it turns off. What does that leave us with? Does it match 21? Yes, it does. So that would then effectively connect to this capacitor down there and then flip and be the opposite of the other one. Okay. I think we got there. This is already an intense, like, this is a lot going on. Oh, man. But technically, I think it works. Due to the complexities of the power supply situation going on here, I think what I'll end up doing, at least when I go to build it, is just build the power supply section, like, and test that, you know, and see if it works, if it can supply heavy current and if it can charge and all that. Because if it can, great. But if not, then we can make changes before we put the whole rest of the board together and waste a bunch of parts. So I'll have to take that into account and add connection points for test. Cool. All right, I'm going to go through and turn off all of these labels. At least for anything that doesn't have it turned off yet. And then I'll duplicate this to the next screen. And then, yeah. And then hopefully you all will be willing to review it. Because it is pretty complicated. All right, so D2 goes up here. Okay, that didn't connect. Oh, it did connect. Wow. And then this goes right there. And then this is our control line. Yeah, let me just delete this and start over here. All right, and then do a net label. Drop that right there and change this label that 8B4_1. And then we're going to delete this, and this, and this. Hold on. What is that? Just bat AB4. Okay. And then drop a wire here and just say And then this is going to get moved. Let's change this to this one right here so we have all the extra space. Let's just drop that right there, okay? All right, battery connectors _1, and then we'll add a new R2. And then we will pull this out. And delete this. And then go here. Add them in. Delete our wires. Just trying to keep all of our jumper names the same. J3, J4. I guess I could just copy it. So D3, J3, and J4. Okay. So copy this. All right, so this one becomes D3. This becomes 2. This becomes J3. This becomes J4. And then everything else in here needs to increment a lot. So C33. And what's the highest R value? 43, 44. What is this one? Why is this titled F38? Anyone else see that? Is this the same resistor? It is. Why is it titled that? 7. Is there an R38 then? Because I think it would have auto-filled one. Let's try R38. All right, well, it looks like we start with R45. Just go through R45. No, apparently we can't. Is there a 40? Oh, there's a 45. Let's try 46. Yep, there we go. R47. Oh, apparently we have one of those. Oh, we have all the way up to like 55. Let's just start with 56 then. R56. R57. R58. R59. R60. R61. R62. R63. All right, is that all the resistors? I think so. And then we got up to Q28, Q29, so we start at Q30. Q31. Q32. Q33. Q34. Q35. Q36. Q38. Q39. All right, I think that makes everything okay. And this one's F38 for some reason. R38's not available. So what's the highest one we used here? R63 maybe? Yeah, so R64. Alright, so the next time we'll have to go through and fill out the bill of materials. But I think, something else we can do is look for, like, a pack. Like this circuit is intense, and there's a lot going on here. We might be able to, like, find a chip with multiple MOSFETs in it, and that way it'll save us some space, because there's so many parts here. If I go validate and then update the PCB, we're going to see just a mess of parts. Give it a sec. Hopefully my stream isn't crashing right now. Validate changes. There are so many. Then I think I can figure all these out. All right, execute. All right, good to know. All right, all these changes executed. Yep, and there's a ton of, I mean, at least they're little parts, resistors and transistors, but there's a bunch of them in here now. So it becomes another mess. It's a good thing it really is a good thing I deleted half those batteries, because otherwise this would have been impossible. And we would have to add so many parts just to get here. Just dragging everything out of the way. I want to get I want to have a really good idea, like, how much space I'm going to need on the board for all this stuff. The answer is a lot. All right. If this screen wasn't saved, does this cause any updates? Yep. All right. I think we're good then. All right. That's probably going to be it for tonight. That was quite the thing. So I think what we'll do next time is see if we can simplify that circuit using just, maybe we can use arrays of, like, some sort of, there probably is like an IC that's a bunch of MOSFETs in one or something that we could use. That would be ideal. Also, I'll read through one of the articles I found that's specifically on selecting MOSFETs for battery balancing, so I make sure I pick something that's intended for this purpose. And then we'll go through it, and after learning how that worked, I'll need to go through and recheck everything where I used a MOSFET just to make sure I got it right. All right. I think that'll be it then. Thank you all for joining me tonight. It's been a good time and a lot of thinking and trying to keep track of everything, but it was worth it. I think we got somewhere awesome in the end. I'll go ahead and save this and back it up. and I will see you all on Thursday. Later.